All right, let's go ahead and look at these guided practice problems where we're going to calculate the average atomic mass based off of percent abundance of different elements or isotopes. So let's go ahead and take a look at this first problem. Notice how we have three stable, naturally occurring isotopes of silicon, and so it tells us right there. And it gives us, it says that we have silicon 28, 29, and 30, and then it gives us their percent abundance. So silicon 28 is 92.21, 29 is 4.70%, and 30 is 3.09%. All right, and it says to calculate the average atomic mass. Now, before we do that, actually, let's go ahead and set up the problem. So this is how you set up the problems. You need to write two columns of information. The first column you want to write is the isotope mass. And so if you take a look, we have silicon 28, we have silicon 29, and we have silicon 30. Now, the second column we want to write is we want to write the percent abundance of each isotope, but we want to write it in decimal form. And so let's go ahead and have a quick review on how to do that. So if we have 92.21%, the way that we make that decimal form is by taking the decimal place and moving it to the left 2 times, 1, 2. And when we do that, we end up with 0.9221. And so we're going to have 0.9221. Now let's go ahead and do the 4.70%. So if we have 4.70%, right, and we want to write the percentage in decimal form, again what we do is we take the decimal and we move it to the left 2 times. So let's go ahead and do that. So we're going to move it to the left 1, 2. And notice we have this space here that we're going to end up putting a 0. And so in this situation, it's going to be 0.0470. Go ahead and write that a little bit better there, 470, okay. And then we have 3.09%, and again, we want to write it in decimal form, and so it's 0.0309. And if you need to, you can write down 3.09 and move the decimal over twice. So again, when we have a percentage and we want to go to decimal form, we move the decimal place to the left 2 times. Now, I want you to just go ahead and pause real quick and take a look at what I just wrote. Again, I wrote the isotope mass, which is this right here, and then I wrote its percentage in decimal form right next to it. Now, notice how we have 3 different isotopes. Some problems, you only have 2 isotopes. Some you might have 4, and so I just wanted to point that out. The other thing, too, is notice how all of these percentages do add up to 100, and so something to keep in mind. Now, the next thing is I want to answer this question right here. What will the average be closest to? So without even calculating anything, what will it be closest to? Well, if you remember from the notes, it's going to be closest to the most abundant isotope. And in this situation, the most abundant isotope is isotope 28 because it has the highest percentage. And so it will be closest to 28. But will it be less than 28? So let me ask you that. Will it be less than 28? And the answer is no, because the average will be closest to the most abundant, but it will also be between the largest and the smallest. And so the largest is the smallest is 28, and the largest is 30. And so it has to be between 28 and 30. So that's just a way to check yourself. We will know that it's going to be close to 28, but it's going to be between 28 and 30. All right, so let's go back to actually calculating it. So if you take a look, we have the isotopes and their percent abundances. And all you need to do is you need to take the isotopes and multiply them by their percent abundance in decimal form. So let's go ahead and do that. And when you do that, you end up with these numbers, all right? So go ahead and pause the video real quick if you want to calculate those numbers on your own. But again, we took our 28 and we multiplied it by our 0.9221. We took our 29 and multiplied it by 0.0470, and then our 30 times 0.0309. So again, what you do is you take the mass, you multiply it by the percentage in the decimal form, and the last thing you need to do is add them together. And that's it. So let's go ahead and add those together. And it's that simple. All right, so I'm going to say it very simply. You take the mass, you multiply it by the percentage in decimal form, and you add them together. That's all there is to it. Now I'm going to go ahead and say a common mistake that people do in this moment. A common mistake that they do is they divide by 3. Because usually when we take averages, we add them all together and divide by 3. But we don't do that in this situation because the percentages themselves are accounting for that. And so make sure you don't do that. So let's go ahead and take a look at the periodic table real quick. So again, this is what we calculated silicon to be. And if we look at the periodic table, you'll see that it is actually pretty close to what it is on the periodic table. Now, it's a little different because who knows where the source of the silicon is, or where the source came from. And so, but it's pretty close though. All right, let's go ahead and move on to the next problem here. So, if you take a look, we're going to calculate the average atomic mass of magnesium using the following 3 isotopes. And notice how it gives us 2 masses. So it gives us the mass here, kind of like if you take a look at this problem here, that's kind of how it gave it to us over here, right? And that's the mass that we used in this previous problem. However, it's also giving us the mass here. And so what you'll be able to do, or what you should do, is if it's ever giving you this exact mass, that's the mass that you should use. All right, oops. So let's go ahead and do this calculation. So again, it's very easy. You take the mass, which these are the masses, and you multiply them by their percentages in decimal form, which all you got to do is move it over twice. So it becomes right there. And then this one becomes here, and this one becomes here. So you take their masses, you multiply them by their percentage in decimal form. So let's go ahead and do that. And after you take the masses and multiply them by the percentage in decimal form, you end up getting those numbers there, and then you just add them together. So let's go ahead and just add them together. And you will end up with 24.3093. And it's that simple. You take the mass, you multiply by the percentage in decimal form, and you add them together, and that's it. Now, I know there's a couple of you where there's some, alarm bells ringing off, and you're like, well, what about sig figs? All right, well, let's go ahead and talk about sig figs. Let's talk about the first problem. If you take a look here, it gives you these numbers here where they're not those exact masses that the other problem gave us. If they're giving you these sort of masses here, what I'm going to say is don't worry about sig figs. If you're just given these rounded masses, don't worry about sig figs. Just bring your answer out to 3 decimal places, because technically this is 1 sig fig, which should make this 1 sig fig, which messes everything up. Now, let's go ahead and talk about this though. Here we're given exact masses. And so if you're given these exact masses, let's go ahead and see how sig figs influences this. If you take a look, when we multiply, we care about the number sig figs. So this has 5, this has 4. In fact, all of these have 4 sig figs. And so all of these answers right here, when we multiply, should have had 4. So we should have rounded this to here, we should have rounded this to here, and we should have rounded this to here. And notice how the first row there, this was rounded to the hundreds place. This was rounded to the thousands, and this was rounded to thousands. And hundredths, thousandths. And so because this only goes to the hundredths, that means our answer should only go to the hundredths as well. And so let's go ahead and do that. So we end up with 24.31. And we put AMU for atomic mass units. All right, so let's take a look at the periodic table, or take a look at the periodic table here and look at magnesium. It's pretty close to what magnesium was. So 34.305 is what the average atomic mass is on the periodic table. And if you take a look, that's pretty close as well. All right, let's go ahead and talk about this problem. Now, this problem is an example of the mass spectrum, or is an example of the mass spectrometer where we have two isotopes of chlorine that are shot down, accelerated down, they're ionized, and they go through a magnet, and it bends, and so the heavier isotope will bend less, and the lighter isotope will bend more. Again, what will end up happening is one of these, whenever you see this, one of these will always be 100, and this one right here is representing 100. And so we need to keep that in mind. So we know that 35, chlorine 35, let's go ahead and write this. The mass spectrometer is saying that it's the greatest abundance, all right? So it's not saying that the percent abundance is 100%, it's saying that it's the greatest abundance. And then what it does is it gives us the percentage of chlorine relative to the percentage of chlorine 35 relative to the percentage of chlorine 37 relative to 35. And so it actually gives it to us right here. So it tells us what that percentage is. So go ahead and pause the video, and I want you to think about what I just wrote down, all right? So go ahead and pause it, think about what I just wrote down. And notice how the chlorine 35, the mass spectrum gives it to us as 100%, and then it says that the chlorine 37 is 32.00%. Now again, these are not the percent abundances. They are rather the percentage that the mass spectrometer gives us, and we need to normalize these numbers. And it's actually really easy to normalize these numbers. Now, when we are normalizing these numbers, what we're doing is we're finding the true percentage of each isotope. So let's go ahead and take a look at how we can do that. And it's actually really easy. I'm gonna go ahead and make a little bit of room here. What you do is you take the percentage that the mass spectrometer gives you and you divide it by all of the percentages added together. And notice, what is the percentage of this first peak right here? It's 100%, because the largest peak is always going to be 100%. But what's the percentage of the second one? It's 32%, 32.00%. And so when we add those together, we end up getting 132. And so what you do is you take the percentage that the mass spectrum gives you and you divide it by the percentages added together, and then you multiply it by 100. And so let's go ahead and type that in our calculator. And then what we do is we end up with 75.76%. Now, all we need to do is do the same thing for the next one. So again, the mass spectrum gives us the percentage of chlorine 37 as 32%, and we take the percentage and we divide it by the sum of all of the percentages, which again, the sum of the percentages is 132. We multiply it by 100, and when you type this in the calculator, it'll end up giving you 24.24%. Now, how can we check ourselves to make sure we did this step correctly? Well, these here should add up to 100. If you had 3 isotopes, those 3 should add up to 100. And if you add those together, it actually equals 100. And so you can check yourself by making sure those add up to 100. Now, if it adds up to 99.99, that's okay. It's just a rounding error at some point. So let's go ahead and finish this problem, though, because this isn't the end of the problem. The problem is wanting us to calculate the average atomic mass. And again, it's just like the previous problems. You take the mass, you multiply it by the percentage in decimal form, and you multiply it, and then you add them together. So let's go ahead and set this up. We have chlorine 35, and we have chlorine 37. We multiply them by their percentage in decimal form, which we just calculated the true percentage. And we take this and multiply it by its percentage. So go ahead and type that in the calculator. And then afterwards, all you need to do is add them together. And that is it. So let's go ahead and review this one real quick. And if you need to, you can rewatch this section. What we need to do is take the percentages that the mass spectrum gives us, and we need to normalize them. And we normalize them by taking their percentages and dividing them by the sum of all the percentages. That's what we did in this step right here. We took each of their percentages that the mass spectrum gives us and divided it by the sum of the percentages. And then we multiplied it by 100 to get the true percentage. This is the true percent abundance of each isotope. And now that we have the true percent abundance, we can then calculate the average atomic mass by taking the mass, multiplying it by the percentage in decimal form, and adding them together. And that's it. If you have any questions, feel free to ask, and look at the answer key to help you with your independent practice problems. You guys have a great day.